let's consider this situation. We have a toy uh, that is positioned in front of a lens, and an image is produced on a screen. They tell us that the image of the toy has a magnification of 2.0. And they are asking us what type of a lens was used. Before going any further, let's discuss what type of lens was used. I'm going back here to the lens equation screen. Remember, whenever I have an object, the natural flow of light is to go through the lens and the other side of the lens, behind the lens. So if the object is in front of the lens, the image is going to be real when it is behind the lens, in the other side of the lens relative to the object. Now, that's when we get real images, when the image is formed and it's going to be able, we are going to be able to project it on a screen, or project it on a retina, or project it on the back of a camera, and so on. Now, if the image is in the same side of the object, or the image is in front of the lens, like the object, then our image is virtual and we cannot project it on a screen. Okay. Now, if you recall, when we worked through divergent lenses, we found that no matter where you place the object for divergent lenses, the image is virtual, the screen image here. Wherever we place the object, we get a virtual image. A virtual image cannot be projected on a screen. So what that means is, if we have an image projected on a screen, our lens cannot be divergent, and our lens has to be convergent. This is sufficient for the answer here. We cannot specify what kind of shape the lens has. It has to have some convex part of it, but the other side does not have to be convex. So we just stick to convergent. It's a convergent lens. Now, what about the focal length of this lens? To find the focal length of the lens, I'm going to have to use the thin lens equation. 1 over dO plus 1 over di is equal to 1 over f. And to be able to do that and to get the correct answers, I need to start by drawing a diagram. So in my diagram, I draw the principal axis, I draw my object, my toy, I draw my lens. Now we know that it must be a convergent lens, so I draw a typical convergent lens. And then I draw where the image is going to be. So it's going to be behind the lens or on the other side of the lens relative to the object. And we know that real images are inverted. So actually, when they gave us a magnification of 2, they didn't tell us if it was inverted or not, but we know that real images from a single lens, when we have only one lens, are going to always be inverted or going to be flipped, meaning that the magnification is going to always be negative. Okay, so now here, this is what we define as our dO, and this is what we define as our di. Let's see which one of these is given in the question. They tell us that, so here they tell us that the lens is 1.5 meters from the screen. So this is where the screen is, where the image is. This is the lens. So they are actually giving us di. DO is not given. They don't tell us where the object is placed. But then they give us the magnification. And we just have determined that the magnification has to be negative. So it's minus 2.0. So we write the expression for the magnification, minus 2.0. That should be equal to minus di over do. From here we can solve for do. do is going to be minus di over minus 2. So that should come out 2.75 meters. Now my length equation gives me, my thin length equation, 1 over f is 1 over do plus 1 over di. So in this case, it's going to be 1 over 0.75 meters plus 1 over 1.5 meters. So putting in the same denominator and adding them up, that comes out 3 over 1.5 meters. So that tells me that my f is 0.5 meters. That's the answer to this question. Okay, in the second question, they say, what would be the image position and magnification if we use a lens instead that is divergent but of the same focal length? So in this case, they give us the focal length as minus 0.5 meters. Now, a negative focal length tells us that we have a divergent lens. If we draw again the situation, this is my object, this is my principal axis, this is my lens, but now I'm going to draw a typical divergent lens. Now, from what we know about divergent lenses, we know that our image is going to be upright, visual, and in the same side as the object. So this would be my do that we found from the previous question, 0.75 meters, and we need to find our di. Okay, so we go ahead and find that. So 1 over f is equal to 1 over di plus 1 over do. So in this case, 1 over minus 0.5 meters is equal to 1 over di plus 1 over 0.75 meters. So 1 over di is equal minus 1 over 0.5 meters minus 1 over 0.75 meters. I'm going to put it in the same denominator, 1.5 meters, so this is 3 and this is 2, so it's going to be minus 3 minus 2 over 1.5 meters, and I find di as equal to 1.5 meter over 5 over negative 5, which is minus 0.3 meters. That's the position of the image, and you notice that it came out negative, telling us that it is in front of the lens, telling us that the image is in the same side as the object. Now to find the magnification, it's easy. Magnification is minus di over do, so we just plug in the values, minus 0.3 over 0.75. Minus and minus, that gives us a plus, and then we have to get 0.3 over 0.75. I'm calculating this in the side, so that comes out to be 0.4 plus 0.4. That's our magnification.